Awesome. Now it seems it's working.
Yeah, cool.
I'll check out anyway on the website. Yeah, it's working. So do you mind waiting a couple of minutes to let some people to come in?
Let's wait till everyone's here.
So let's wait. We have some people on Zoom and we should get some people connecting. Pregunta, ¿alguien puede chequear? Agradecería en el YouTube del DCC si se ve esto, que diga que esto está funcionando, sería muy agradecido.
Sí, está funcionando.
Ya. Okay, Alan, this is what I'm going to do. I want to introduce you first in Spanish, and then I will reintroduce you in English, okay? So to explain the audience so they can make questions in Spanish if they want in the YouTube chat, and then I can translate if they want straight to make these questions straight in English, that's fine too. And I suppose that you prefer questions to be at the end of the talk?
Yeah, I mean, yeah, probably best to wait till the end.
Okay. Great. Ok. Hola a todos y todas. Bienvenidos a este seminario del Departamento de Ciencias de la Computación y del Instituto Milenio Fundamento de los Datos. Hoy día tenemos el privilegio de tener una charla de Alan Ansell, estudiante de doctorado de la Universidad de Cambridge en el Laboratorio de Procesamiento de Lenguaje Natural. Alan es oriundo de Nueva Zelanda. Él hizo sus estudios de pregrado allá en la Universidad de Auckland y sus estudios de magíster en la Universidad de Waikato, donde yo tuve la suerte de ser uno de sus profesores guía. Y es un trabajo muy interesante en temas de language models y cosas con polisemia. Y este trabajo fue recién aceptado en un congreso que se llama EACL, que es el European Congress de NLP. Así que lo invité hoy día para que nos presente su trabajo. So in English, briefly, this is Alan Ansell. He's currently doing his PhD at the University of Cambridge in the NLP group. And he's originally from New Zealand. He did his master's studies there and his undergraduate studies there as well. He studied undergraduate studies, I think, in engineering at the University of Auckland. Then he came to the University of Waikato, where I used to work to do his master's student. And I had the privilege to work with him along with Bernhard Faringer to be his co-supervisor. And he did a very nice job work on language models and polysemy. And he managed to publish his work at EACL, which is a very important conference on NLP. So that's it, Alan. Welcome.
Yeah. Thank you very much for the introduction, Felipe. So, most modern NLP models learn word embeddings, or recently this sub-word level embeddings used in BERT, for example, have become popular. But this kind of conflicts a bit with our linguistic intuitions, because there are many words which have several meanings, which might be completely unrelated, and these are all conflated into a single vector, a single point in semantic space. And this is called the meaning conflation deficiency. So this plot is an illustration of this effect. So for example, the word right has several meanings in English. It can mean right as opposed to left, or right as opposed to wrong, or it can be a noun meaning a freedom, rights and freedoms. And it even has, for example, a political meaning, left wing and right wing. So when we represent right as a word vector, we find that it is close to the word vectors for left and wrong. They're both synonyms of right, but the words left and wrong are therefore also close to each other, even though they have no relationship. So before about 2018, there was an area of research where people tried to learn embeddings for individual meanings of words, which are called sense embeddings. And this was used, for example, for word sense disambiguation and word sense induction, where you try to determine in which sense a word is being used in a given context. And there are other potential applications for sense embeddings, like, for example, constructing dictionaries or other lexical resources for low resource languages, for example, and also in cross-lingual embeddings, which are used in machine translation, for example. But since then, NLP has seen the emergence of contextualized embeddings. It's like Elmo and BERT, and maybe people assumed that these contextualized embeddings capture the meaning of words in context, and so polysemy maybe isn't such a problem anymore. But even these models still rely on word or subword level embeddings. So the meaning conflation deficiency is still potentially a problem. So we kind of revisit the question of whether sense embeddings are still useful. So our model is called PolyLM. So it's a fully sense-based contextualized model, and it's unsupervised. It doesn't rely on any lexical resources like WordNet, which means that it can be applied to any language for which we have unannotated data. So I'll start with some definitions. So suppose we have a vocabulary V, and each word W in the vocabulary has a set of senses SW. And we'll assume that no two words share the same sense. So then we have the set of all senses, or sort of sense vocabulary is the union of the senses for each word. So the key idea behind our model is that the probability of a word occurring in a given context is equal to the sum of the probabilities of each of its senses occurring. So we have that mathematically notated here. Probability of word in a context is the sum of the probabilities of its senses. So this is useful because it lets us formulate the problem of learning word senses as a language modeling problem, because in language modeling, we're trying to maximize the estimated probability of a word in a given context. So in fact, like BERT, we use masked language modeling to train PolyLM. So we have one embedding per word sense, rather than one embedding per word as we would have in a word embedding based model. So one problem we have is that at the input of the model, we don't know which sense of the word is being used. So we represent a word as like a weighted sum of its sense embeddings, and the weights are learnable. So we feed these embeddings into a transformer encoder, like a BERT implementation of the transformer encoder, and we produce a corresponding sequence of output embeddings. And then we produce a distribution over the possible words that could occur in a masked position, except it's not a distribution over words, it's a distribution over word senses. So we multiply the embedding matrix by the output embeddings and apply softmax to get a distribution. So then the probability of the target word appearing is the sum of the probabilities of its individual senses occurring. So this corresponds to this formula here. And of course, we maximize the estimated probability of the masked words occurring. So this is the most basic form of the model, but there are a few improvements that we can make. So one of the issues is we have to assign, kind of guess the number of senses for each word. And since this is an unsupervised method, we don't really have any prior information about this. So we just guess a kind of large number, 8 senses per word. And we choose a large number because we want to make sure that we capture all of the senses of the words which have many senses. But this leads to the problem that words that have few senses, many of the sense embeddings will end up converging to the same sense. So, for example, if we have a word that only has one sense, but we assign it 8 senses, then all of those senses will converge to the single sense of the word. So to deal with this problem, we add an additional term to the loss function, which we call the distinctness loss. And this encourages only one sense of a word to have a high probability in any given context. So the idea is if the model consistently thinks that two senses of a word are both possible in a context, and that means that those senses are kind of the same. So so this is the distinctness loss, and I won't go into explaining this in detail, but there's quite a lengthy justification of this in the appendix of our paper, which you could look at if you're interested. So the second improvement is what we call the disambiguation layer. So you might have noticed that at the input of the model, each word is kind of still represented as a single embedding. So it's kind of like a word embedding, even though it's made up of the sum of the sense embeddings. But here we're still potentially having problems with meaning conflation. So we add an extra small transformer layer at the input of the model, which tries to determine which sense of each word in the input applies in the context. So we input the embeddings into the transformer encoder and we get out some embeddings, and we use these embeddings to form a distribution over the different senses of the input word. So this is kind of like an attention mechanism, because we take probabilities over each sense, and then we use the probabilities to calculate a weighted sum of the sense embeddings. So what we could do is simply take the sense embedding with the highest predicted probability in the context, but a function like that is not really differentiable or not smooth, at least. So instead we take this weighted sum and input that into the main transformer encoder. So we trained 3 different versions of this model of differing sizes. So embedding sizes of 128, 256, and 384. And so the largest model has 90 million parameters, which is slightly less than BERT base. And the models are also, so I think the BERT models are trained on about 10 times as much data as our models, but we didn't have enough, didn't have Google's massive TPU data centers, so our models are not trained for quite as long. So this is some output of the PolyLM models, which kind of illustrates the advantage over word embeddings. So now we have several embeddings corresponding to the different meanings of right. So we have one embedding that is the right as opposed to wrong meaning, one sense which picks up the political sense, and so on. So this suggests that we have kind of overcome the meaning conflation deficiency to some extent. So we do a quantitative evaluation on word sense induction, which is kind of like the unsupervised variant of word sense disambiguation. So you're given a number of contexts in which a given word like right occurs, and then you have to group the instances together into groups where the focus word like right has the same sense. So if you were given a bunch of instances and in some of them right was used with the directional meaning and a bunch where it was used as right as opposed to wrong, then you would have to separate those instances out. So it's very natural to do this with PolyLM because you just run it on each instance and group them according to which sense of the focus word had the highest predicted probability. So the results are shown here compared against the method of Amrami and Goldberg, which was the previous state of the art. So the large model, I'll explain a little bit Ambrami and Goldberg's method uses a technique called substitute vectors, which it obtains from BERT's output embeddings. So, but our model, the large model, achieves state-of-the-art on both datasets, even though it has only or less than a third of the number of parameters as BERT large, and it's trained much less. So this is a little ablation study which shows the benefit of each component. So if we remove the distinctness loss or the disambiguation layer, we observe quite a big decrease in performance. So both of those improvements are quite important. So another thing we can do with PolyLM is we can take only the outputs of the disambiguation layer and use them for word sense induction, and we achieve quite good results, even though the disambiguation layer is only has a very small number of parameters. So I guess the conclusion here is that there's still potential for sense-based models. So the previous assumption that sense embeddings are obsolete due to contextualized models isn't really correct, because we can PolyLM seems to achieve a better understanding of word senses than BERT, despite having far fewer parameters. Yes. So thank you for listening to my presentation, and I'm happy to answer any questions now.
Thank you, Alan. Many thanks for your talk. Any questions o preguntas en español? Yo puedo traducir si quieren.
I have a question. Can you hear me, Felipe? Alan?
Yep.
Yes. Thank you, Alan, for the presentation. I have a very simple question. How do you compute the embedding for a single word in your model? Because you are like projecting PSNE, and I wonder how you just compute for a single word.
So are you referring to
I mean
this diagram?
You have a transformer model, yes? So that usually gives you a vector for each word in a context. So if yes. I just want a word for right that you are plotting here, for example, how do you compute that?
So it comes from the embedding matrix. So remember, each word has several senses. So in this diagram here, each of the points refers to one of the sense embeddings for right in this embedding matrix.
So I understand better now that then you actually use this transformer as a auxiliary method, because what you actually want is that embedding matrix?
Yes, but the contextualized embeddings are also useful. So for example, when we're doing word sense induction, we get a probability distribution over the senses produced from the output of the transformer, and then we choose the sense of the word which has the highest probability in the context.
Okay. And can we access this embedding matrix in some URL or?
So
you have it published somewhere?
Yeah, the models are on GitHub. So
Good.
actually,
Okay, I will ask Felipe later for a link for the models. Thank you very much.
Thank you, Jorge. Any more questions? ¿O más preguntas y yo traduzco? So I have a question, Alan. I work with you for a year, but I still have many questions. So that talks good about the work, maybe not good, talks too good about me. But so still the number of senses is fixed here.
Yes.
So what happened with words that have less than 8 senses in the end? So what happened is these senses that are not used? How can you tell apart the useful and the useless representations you get in the end?
So what happens is, due to the distinctness loss, usually only one of the senses of the word will ever have like a high probability predicted. So all of the other senses will almost never be predicted. So during training, you can keep track of the average probability of each sense. So when you see that a word has only one sense that has a high probability, then you can conclude that that word only has one real sense.
Thank you, Alan. I have a question from the YouTube chat.
Okay.
So the question is given by Mauricio Palma. So I will read the question in Spanish first, just for the audience. La pregunta es, ¿por qué es útil más simple la suposición indicada al comienzo de la charla de que dos palabras no comparten senses? ¿Se pierde generalidad? So the question is, what about the initial assumption that two different words should never share senses? Is there a loss of generality by making that assumption?
So the reason for it is how would you decide which pairs of words should share a sense? Because if you have an unsupervised method, then you have no way of guessing in advance which words should share senses. But actually there are potentially ways you could have a model where all words can have a given sense, but then you need a very large matrix which gives you the probability of a given word having a given sense. So the dimensionality of the matrix would be the size of the vocab times the number of senses, which is too large to be very practical. So yes, there is kind of a loss of generality, but it's necessary for efficiency, really.
Thank you, Alan. I have 2 other questions. So one question, imagine I'll give you an hypothetical task and I would like you to think how easy it will be to use your method for that. What if I give you the task in which I give you a corpus, just a corpus, and I ask you for each word in the corpus, tell me how many senses does this word have? How easy it will be to solve that task with this problem, with this model, without any extra fine-tuning?
It should be pretty easy because, as I explained before, the distinctness loss means that senses that aren't used, their probability goes to 0. So you can kind of count the number of senses for a word that actually occurs in the corpus.
But still, you will need to fine-tune some threshold to tell regarding these probabilities you have, which ones tell. You need to turn this real value number into a decision, into a binary decision, if this about the exact number of senses.
Yes, but that doesn't involve modifying the model. It's just an independent parameter which you would choose, right?
But do you think if you use something very arbitrary there, you will get good results? Yes, you say if the probability is greater than 0.5, then should be a sense or something like this.
I think it's a reasonable thing to do. I can't promise anything about the results, but that's how I would do it, I suppose.
Awesome, awesome. And then it's my final question, Alan. So there are some laws about polysemy, the frequencies laws that tells something. I've seen some, I'm not an expert, but I've seen stuff that's saying that some frequent words are more likely to be polysemous than non-frequent words. And I don't know how you think this kind of properties of language could be incorporated as prior information to your model.
Yeah, so that's called, I can't remember the name of it. It is a famous law in linguistics, I guess, but the name escapes me right now. So yeah, what you could do is you could assign a larger number of senses to more frequent words. And actually, something I didn't mention is that words that are very infrequent in the corpus, we only assign them a single sense. So just avoid the total number of senses from being too large. So to a very limited extent, we do incorporate that prior knowledge in the model.
Great, thank you. ¿Más preguntas? Any more questions?
Hi, yeah, I have a question. Thanks, Alan, for your talk. It was related to the last point that you just mentioned. When you said that you assigned by default 8 senses for each token, I thought that maybe that could lead you to some sparsity problem, because now you have like a number of vocabulary or certain amount of embeddings that you have to train, but now you have to multiply by a certain number of senses. And I was thinking about if it could be useful to integrate some kind of hybrid method. So you integrate previous knowledge about, I know that these words in particular tend to have many senses. So I want to focus on these words, and these other words just have 1 or 2 or not 8, and there might be words with more senses, right?
Yes. Yes, so for example, you could look at WordNet, for example, or some sort of dictionary, and for each word, see how many senses it has in WordNet, and then assign that many senses to the word. Yeah. But one issue is that there are actually a lot of words that do not, like WordNet does not contain all of their senses, like names, for example, aren't well represented in WordNet. But yeah, in general, I think this is a very reasonable thing to do, but I guess we wanted to keep it unsupervised, which is why we chose to just go for a fixed number. Yeah.
Great. Thank you, Alan. I think there are no more questions.
I have just a last one.
Okay, go ahead, Jorge.
If I just want just one embedding for a word, does it make sense to just sum, for example, all the meanings in your embedding matrix, or it doesn't make any sense?
Yeah. Yes. So remember, at the input, we have to represent a word with a single embedding. So we have this weighted sum of the sense embeddings, and the weights we learn during training. So if you wanted to represent a word single embedding, would make sense to take the weighted sum using those parameters we learn during training.
Cool. Thank you.
So do you recall, Alan, for words having few meanings, if those weights were close to zero for the redundant sentences?
I'm not sure if I ever actually investigated that, but I would expect that they are. That would, yeah, I think I would guess they are, but I can't say for sure.
Yeah, it will be interesting to explore a bit more what happens with this, that kind of garbage vectors. What does it get stored?
Yeah.
What sort of stuff? Yeah. Great. Thank you, Alan. So maybe you can tell us, we have a little bit of time. Maybe you can tell us a bit, what are you working on right now?
Okay, sure. So
briefly.
So I'm working on cross-lingual transfer. So for example, I guess one of the big issues is that there are a few languages that have a lot of data, but many that have very little data. So suppose you want to do part of speech tagging or parsing in some language, but you don't have any sort of linguistic experts available in that language who can produce training data, then what you would like to do is, suppose you have lots of English or Spanish part of speech tagging or parsing data, you can train a model on that data and then do cross-lingual transfer to make it work in a different language in which you have no data on the task in question. So you might have heard of embed, for example, or multilingual BERT, which is trained in many languages, well, unannotated data in many languages. So there are various ways that you can then sort of fine-tune that model on for a particular task using data in a high resource language, and then make it also work in a low resource language. So yeah, the particular technique which I've been using lately is called adapters. So which is where you actually insert some new layers into a multilingual model and fine-tune those to specialize the model for a particular language or task.
What sort of results are you getting so far?
So something we got some quite nice results for is we discovered that suppose you train on the target task in a single source language, you get some results. But then if you train using 2 different source languages, even if the total number of training examples is the same, but they come from 2 different languages, you get a really big improvement in performance, even if the target language is not related to either of the source languages. So yeah, I think it's a really interesting finding.
Okay, so I hope we can invite you again in a couple of months. For you to talk about
Maybe.
this.
Yeah, hoping to have a paper at some point in the next few months. So
excellent.
Yeah, maybe then.
Excellent. Yeah. Good luck with this. Great. Thank you, Alan.
Thank you for inviting me.
Yeah. See you then. Thank you. Gracias a todos. Nos vemos para la
Very
próxima sesión de RL. Chao, chao.
Ciao.
See you, Alan.
Bye, Felipe. Bye, everyone.
You too.